of this research, innovative biofuel. I believe peracetic acid in combination with fungal synthesis could fill this role. Here are the things we'll be covering. I endeavored to discover an optimum approach to producing the most energy from biomass by employing the most efficient processes. For the past 6 years, I've studied biofuel technologies that have the potential to alleviate the current global energy crisis. During these 6 years, the price of fossil fuels has continued to skyrocket, causing shortages and financial hardships for millions of families and societies around the globe. After experimenting with used cooking oil in the 6th grade and algae in the 7th, my research has led me to the conclusion that cellulosic biofuel from farm waste has the best potential to alleviate the current global energy crisis. Cellulosic biofuel is not only renewable, but also remarkably clean burning, reducing greenhouse gases by up to 86%. The traditional methods of biodiesel production from animal fat, vegetable oil, and algae create conflict with the food industry and seize extensive land for cultivation. Due to high energy yields and low land requirement, microbial lipids represent a sustainable and viable alternative to traditional biodiesel production. Unlike ethanol, microbial lipids, as a drop-in fuel, are compatible with current engines and can directly replace jet fuel, diesel, and gasoline, thus minimizing compatibility issues with existing infrastructure. Lipids also hold a myriad of applications in cosmetics, food, and nanotechnology. Initially, I hypothesized that compared with previous year studies of enzymatic hydrolysis and bacterial fermentation, peracetic acid hydrolysis coupled with fungal biosynthesis will yield the most energy in the form of lipids and ethanol. Here's a flowchart depicting the process I followed. This research investigated the use of peracetic acid to remove lignin and break down cellulose in fungal biosynthesis, to retrieve sugars and synthesize them into ethanol and lipids. This innovative approach could be a sustainable method of converting cellulosic biomass into renewable energy. These studies are vital because finding the best processes is imperative to a cost-effective cellulosic energy program. To begin, I ground the corn stover and aspen to the size of 50 micron particles. 5 15-gram samples of each were isolated for the peracetic acid pretreatment. 2 of these were reserved for use as controls. I reacted glucose pentaacetate and hydrogen peroxide with sodium hydroxide to a pH of 11.5 to convert the pentaacetate into peracetic acid. 3 solutions were prepared to generate peracetic acid in 5%, 10%, and 25% strengths. 1 sample of each biomass product was treated with the 5% solution, 1 of each with the 10% solution, and 1 of each with the 25% solution. The samples were placed in a water bath at 70 degrees Celsius for 2 hours, washed with deionized water until they reached a pH of 7, and then dried overnight. To determine the efficacy of the peracetic acid pretreatment, I subjected all the biomass to a standard acid hydrolysis, and then determined the Clayton lignin utilizing this formula, and established percentages of glucose and xylose using high-performance liquid chromatography, or HPLC tester. Understanding the composition of the biomass is vital to designing the perfect method of pretreatment, hydrolysis, and fermentation that will lead to production of the highest energy yield and the most cost-effective and sustainable system. Lignin, a tough polymer that surrounds cellulose, is the primary impediment to large-scale cellulosic biofuel production. Employing the higher concentrations of peracetic acid, I effectively removed it, leaving only 6% in the corn stover and 9% in the aspen. Most pretreatment methods, such as dilute sulfuric acid at high temperatures, disrupt cell walls to expose sugar polymers, but fail to remove the lignin. In contrast, peracetic acid reduces the molecular weight of lignin polymers by cleaving B-arthyl ether bonds in both carbon-carbon and carbon-oxygen bonds linked to the aromatic rings. Then peracetic acid simulates several reactions that increases the water solubility of lignin. The dealkylation of O-methyl groups, introduction of hydroxyl groups to aromatic rings, and cleavage of aromatic rings into muconic acids. These reactions increase the polarity of lignin and create water-soluble lignin fragments that can be washed away from the lignocellulosic biomass. These unique qualities allow in situ generation of peracetic acid to remove over 69% of the lignin from both biomass products, enabling the release of 97% of all the sugars. These values are extremely promising when considering large-scale cellulosic biofuel production. Now I was ready to begin the fungal biosynthesis process. First, I create the culture medium using the following list of materials. Utilizing a scale precise to 1/10,000th of a gram, I isolated 3 2-gram specimens from each sample of pretreated and untreated biomass, for a total of 36 samples. I added 100 milliliters of the culture medium to all 36 flasks and autoclaved them for 60 minutes at 1.2 atms and 121 degrees Celsius to remove all undesirable organisms. I added Fusarium equiseti fungi to 40 milliliters of distilled water and then inoculated each of the 36 specimens with 1 milliliter of the fungal solution. All 36 cultures were incubated at 27 degrees Celsius and 150 RPMs for 10 days to create the ideal environment for optimal fungal growth and lipid and ethanol synthesis. Fungal growth after 10 days. After 10 days, the specimens were centrifuged for 10 minutes at 7,000 RPMs to separate the filtrate from the fungi and remaining biomass. To establish ethanol percentages, 40 milliliters of the filtrate was retained, resulting in the elimination of 60 milliliters of superfluous filtrate. The biomass and fungi were dried overnight at 105 degrees Celsius and then ground with a mortar and pestle to a fine powder. I added 0.3 grams of each of the ground materials to 36 test tubes and subsequently prepared a mixture of 2 parts chloroform to 1 part methanol. 10 milliliters of the mixture was added to each test tube and they were shaken at 150 RPMs for 16 hours. Next, 2.5 milliliters of distilled water was added to each test tube and they were centrifuged for 7 minutes at 7,000 RPMs. The upper layer was then discarded, but the lower layer was retained and filtered into a new test tube. The remaining liquid was evaporated using nitrogen gas, leaving the lipids. Individual lipid results. The last step was determining ethanol percentages through the use of high-performance leukochromatography, or HPLC tester. To do this, I calibrated the HPLC by running pure samples of ethanol. The biomass samples were then filtered and placed in the HPLC in specific locations that identified them by material and as A, B, or C sample, and processed to determine their ethanol content. Portrayed here is an example of data generated by the HPLC. The largest peaks represent the solutions added to the basal media. The rightmost peak, signified in red, represents the ethanol yield. By measuring the area under the peak, I can extrapolate the ethanol production through completing a graphical analysis of the results. Individual ethanol results. After performing the peracetic acid pretreatment and fungal biosynthesis on the corn stover and aspen, and after examining the high-performance liquid chromatography test results, it was concluded that these processes are viable methods for large-scale lipid and ethanol production. This was based on high lipid and ethanol yield. The removal of lignin, a recalcitrant biopolymer that surrounds the inner cellulose, allows Fusarium equiseti to effectively synthesize both hexoses and pentoses, 2 different varieties of sugars, into ethanol and lipids, markedly increasing the energy production. Most modern processes can only effectively synthesize hexoses, leaving approximately 30% of the sugars untouched. This is a problem that needs to be addressed when considering large-scale cellulosic biofuel production. Thus, the 3 samples of 5% peracetic acid performed poorly, producing significantly less ethanol and lipids than either the 10% or 25% concentrations. The 25% samples had a dramatic increase in ethanol and lipid yield that surpassed any method previously tested. In fact, when coupled with fungal synthesis, it attained over a 93% theoretical energy yield. Furthermore, this process can generate increased energy yields between 34 and 37% over the current industrial standards employed by DuPont and POET, the largest cellulosic biofuel producers in the United States. Employing 1 ton of biomass, DuPont and POET can produce approximately 7 million BTUs of energy. In stark contrast, these processes generate 9 million BTUs, a 37% increase. Scientists estimate that the United States can sustainably gather 450 million tons of biomass per year, while still meeting the nation's food, feed, and export demands. Employing the novel processes described in the study to all available biomass, the United States could produce roughly 4.2 quadrillion BTUs, 5 times the energy needed to fuel the entire transportation industry, which accounts for over 30% of energy consumption in the United States. These figures strongly support the premise that a dynamic biofuel industry would be capable of sustainably filling the needs currently met by gasoline. But on top of that, we can reduce greenhouse gases, save time, save money, and protect our world. I'd like to thank Dr. Riki Tishner from the University of Minnesota for her generous and steadfast assistance with equipment and materials and with informed counsel. I further express gratitude to UM's Dr. Bohue and Mian for their able assistance with fungal research.